Tell me about wavelengths and frequencies. What's going on there?
So light is kind of like the byproduct of this hurly-burly, frisky puppy kind of energy of matter. Or you might look at the chair you're sitting on and think it's solid and motionless. But if you're peering down to the atomic level, you're actually able to see all of the movement of those atoms.
When I'm looking at Chuck, he's maybe 2 feet away. I don't see him as he is. I see him as he once was 2 billionths of a second ago.
And believe me, I'm a changed man now.
What is data sonification?
All of these different elements have been mapped with color. So instead of just looking at it as a visual, we're going to hear those mapped to sound.
And now, please welcome to the stage your personal astrophysicist and host of StarTalk, Neil deGrasse Tyson.
Welcome. Thanks for this warm welcome. Tonight's topic, I don't know if you know this in advance, is titled Windows to the Universe. Everything you ever thought you didn't know about windows to the universe, you're going to hear tonight, just to be clear. And we're going to talk about the James Webb Space Telescope, X-ray telescopes, and we're even going to see how we can extract sounds from data in space. And we're going to see how all of that happens because we have one of the world's experts on that with me this evening. Before we bring her out, let me introduce my co-host. That will be Chuck Nice. There it is, man.
Hey, buddy. How are you?
All right. There you go.
Thank you. Thank you.
We're going to introduce now our official expert guest for the evening. She's an author and an expert in astrovisualization. Bet you didn't know that was a word, did you? But not only that, beyond astrovisualization is a dimension of that called data sonification. Welcome to the stage, Dr. Kimberly Arcand. Kimberly, welcome.
Thank you.
Hello.
Hi.
All right. So you're a visualization scientist. That's a thing.
It's a thing.
And
Who knew?
It's not an accident that our field, astrophysics, makes its way to the pages of books and headlines and the front page articles, because we not only have, I think, cool content, we have cool images. And you've taken it even to new heights. So you are, what do we call it, an emerging technology lead.
Yes.
That's a thing.
It's a thing.
For the Chandra Telescope.
Yes.
Up at the Center for Astrophysics in Cambridge.
Yep.
So the Chandra Telescope specializes in what?
X-rays. So instead of taking infrared images like the James Webb does, Chandra looks at X-ray light. So this super high energy light that's out there in the universe.
Okay, so we'll get back to that. Just lay the stage for that. And you are the principal investigator of NASA's Universe of Sound Data Sonification Project.
Yes.
Okay, so you're just all up in this. Yeah, okay.
Yes.
All right. And you are author.
Yes.
This is just a stunning book, Light, the Visible Spectrum, and Beyond. This is just an expensively produced, just look at this. It's an expensively produced book. So congratulations on that, and that effort. And you have a co-author on this.
Megan Watsky.
Megan Watsky.
Yes.
And who's Megan Watsky?
She is my science bestie. She writes all of the press material for the Chandra X-ray Observatory, and she's just awesome. Okay.
So we all might wonder, as did I till I met Kim, what is data sonification? So why don't we just sort of give a taste of it, and then we'll dig in deeper in a few moments. Just check this out. So that was real data.
Real data.
Real data.
So it's basically the CALM Act for the universe.
Yes. Funny, we've actually had people approach us asking for like meditative versions of this that they can use for those apps. Yeah.
That makes sense.
So those the aliens who wanted
No,
to...
humans.
Okay,
Humans.
to do that.
Humans want that.
Aliens with anxiety problems.
Maybe. Yeah.
All right, so before we get up in that,
Yeah.
let's just lay some groundwork so we're all on the same page, speaking the same language. All right, so just a brief intro to telescopes and electromagnetic energy. You live in that space. And so we can look at beautiful images of the universe. And what are some fundamental things just up front you should be able to tell us about it? Because we know, for example, these objects are far away. When I'm looking at Chuck, he's maybe 2 feet away. I don't see him as he is. I see him as he once was 2 billionths of a second ago.
And believe me, I'm a changed man now. Just letting you know.
2 billionths of a second
2
ago.
billionths of a second ago, I'm telling you, I was awful.
So that's like not much time. But as you go out into the universe, of course, the time delay is much, much greater. We have to factor that in to what we're saying about what we think is happening now versus whatever it once happened. But also, we are seeing the universe through telescopes as our eyeballs would receive this information. And our eyeballs are sensitive to what we call visible light. And yeah, visible light we love our visible light, but how does visible light compare to the rest of the electromagnetic spectrum?
It is a very, very tiny portion. It's like if you're into the piano, if you play middle C and a couple keys on either side, that's your visible light. And then all the rest of those 88 keys, that's everything else that we're missing out on in the world, in the
So
universe.
our eyes suck.
They do. They do.
Yeah, we have awful eyes.
Not the best. Not the best.
But we didn't know that until we discovered other bands of light outside of that spectrum.
Yep.
And there's a fun story about the discovery of infrared, all right, which is just outside of the red. It was William Herschel. After Newton had laid down the spectrum, red, orange, yellow, green, blue, violet, he asked the question, and this is what separates great minds from like everybody else. He wondered if each color had a different temperature. So he took a thermometer and put it in, he had a prism and the light coming through, and there's like the rainbow on the table, and he put the thermometer in each color. But you need a control thermometer, all right? Because you don't know if what's happening to that thermometer is also happening just in the ambient air. So he put a thermometer to the side of the spectrum where there was no light, just off to the red. There's nothing there. Puts a thermometer there. And then he goes to check and to compare. And he discovers that the hottest thermometer was the one where there was no light coming in.
And 100 thermometers later.
And so, is it a mistake? Is it a? And he concluded that the sun, because that was sunlight coming through the prism, must be emitting light, quote, unfit for vision. That was the first description of the discovery of infrared. Infrared light. More on infrared later, but we can't see infrared light.
We can't.
More on this. So our atmosphere is transparent to visible light. And what's the best evidence of that? What do you think?
I think the fact that we see the sun.
Yes.
Yes. Good.
I was going out on a limb, guys.
Good one, Chuck.
Yeah.
In broad daylight, you can see the sun.
Yeah, exactly.
And we see visible light.
Right.
And it comes through the atmosphere. But that atmosphere is not good for other bands. So what are challenges we have, and how do we overcome it?
Right. So like Earth has this super protective layer, thankfully for us, right? But that means X-ray light can't get down here. That means ultraviolet radiation, only some can get down here, right? So there's all of these things that we have to do. We have to launch telescopes up to space.
Above Earth's atmosphere.
Above the atmosphere.
The absorbing
in order to catch
layers.
it. Yep.
Okay. And of all of the bands that don't make it through, visible light makes it through. We are sensitive to visible light, so it's a nice matchup.
It is.
And we evolved under this star, the sun, under this atmosphere of Earth.
Exactly.
It would be cruel if we were sensitive to like microwaves or something and nothing came in a microwave. We'd just be blind.
Is that the reason why our eyes suck?
It's more reasons why our eyes suck. So the Hubble telescope is one of the great observatories that was launched above. And that saw what kind of light?
Mostly optical, but also a little infrared and a little bit ultraviolet.
Okay. And the Hubble, we all remember the Hubble telescope. It's still up, launched in the early 90s.
Yep.
And it was stupefying. I remember just losing my breath every time I saw one of the images that was published. And we have one of the early ones here. What can you tell us about this?
The Hubble Deep Field. And what this is so beautiful, it's because they didn't really think anything was there, right? They pointed the telescope at it for a period of time, wanting to see what would happen.
A blank part of the sky.
A blank part of the sky, not knowing that this was what they'd get. And it's just teeming with all of this stuff, right? All of these galaxies that are far, far away. And it's just a whole other glimpse into our universe that we had never had before Hubble. It really set the stage.
In fact, that observing effort would have never made it through the telescope allocation committee.
Oh, right. Which is one of those things, right?
Right.
Like you need to have time for play.
Right. The serendipity of just, let's just look up and see what's there.
See what happens.
Yeah, if you apply, say, I want to find an empty spot of the sky and just stare at it.
But I can do that. I don't really need a grant or a government permission.
Right. And so this was done by the director of the observatory, with our foresight, each director has, I'd forgot, was it 10%, 15? There's some percent of the total allocated time called director's discretionary time. The director can just
do whatever he wants.
Do whatever the director wants.
15%?
It's just some
I think
percent.
it's 10, but yeah, it's something. It depends.
That's a lot, though, when you think about how limited the time of a telescope
But
is.
it paved the way, because now other telescopes do that same thing, knowing that they'll be rewarded.
It set the stage for other telescopes. And it's not just what the director wants. The director might see a proposal that is a little risky, but everyone thinks it's too risky. They say, let's do it.
Yep.
So they can pick other people's research. Yeah. And so that's what made that image.
Do we know that? Who is this? Because let me tell you something. That guy has cojones. Because you're like, I mean, just think of it. He's like this. Okay, I want to take the telescope and I would like to look at nothing.
Yes, exactly.
The most powerful telescope.
Oversubscribed by a lot. Like everybody wants to use Hubble, right? And so to take the time to look at nothing. And to turn it into something.
But that,
poetry there is lovely.
Risk, the gamble that this guy, because he would be known right now if we were looking at a blank screen as the dumbest man at NASA ever.
Right. But this came up. And just as a reminder, nearly everything on this image is an entire galaxy outside of the Milky Way. There's a couple of stars. Those have the little spiky features. But in the Hubble deep field, forgot how long the exposure was, but it's seeing galaxies way out to the edge of the universe. We were happy with that until what?
Well, I would say until Chandra came along and did it too, and then the James Webb Space Telescope came along.
The James Webb Space Telescope.
Even deeper.
Okay, so let's compare what Hubble sees with James Webb. And one of the most iconic images was the Eagle Nebula. Right. Talk us through these two images.
Yeah, so I love hearing all the oohs and ahs from the audience. You're the best audience ever. Okay, so we're looking at this beautiful area of star birth, right? These tall columns of gas and dust. They're just teeming with new baby stars that are being formed. And then you can see on the Hubble image, which is a relatively deep image on the left, right? You can see that there's really a dearth of stars. You can see where those clumps of gas and dust, where those stellar nurseries are kind of, they look almost like attached and really kind of connected. And then you look on that same field of view from the James Webb Space Telescope, and what are you seeing? Like, it's sparkling with stars, right? You can capture all of that sparkling amazingness. And then you're also starting to see that there are like little newborn stars. Those are some of those really bright red patches that you can see as well. And again, now you're seeing more about the inherent structure of those tall pillars and gas and dust where the stars are forming, and the population of stars around them, because stars may be born in a nursery together, but then they kind of grow up and go out on their way. And you're kind of seeing some of that happen, which is, I think, pretty awesome.
And so why is infrared good for that?
Because infrared is like being able to see through things, right? It's kind of like, well, I can't use the X-ray analogy because I'm going to use that later, but it's about being able to peer through in a very different way and capture an entirely different kind of phenomena type, which is lovely.
So Hubble could not see into this gas cloud.
Right.
So it looked like there's not much there.
Right.
It's just a dark area of the sky. you pull out JWST,
Yep.
and that cloak is transparent to it as though it's looking through a window,
Right.
just a glass screen.
It's like you've cleaned the window, right?
Yeah, okay.
You know?
So infrared has that ability to look through it. So tell me about wavelengths and frequencies. What's going on there?
So light is kind of like the byproduct of this hurly-burly, frisky puppy kind of energy of matter. Or you might look at the chair you're sitting on and think it's solid and motionless. But if you're peering down to the atomic level, you're actually able to see all of the movement of those atoms, right? And so light is that byproduct of all of that activity. So like a photon, a packet of energy, is kind of like leaving the scene of the crime because there's a collision between those charged particles, for example. And then when you're trying to characterize light, you've got frequency and wavelength, essentially. If you picture a small pond and you have a steady drop of stones into that pond, and that will cause that beautiful rippling out. So the steady drop of stones will keep it constant for us for this little exercise. So you've got these beautiful ripples going out at these beautiful speeds. If you're going to time, essentially, the time it takes for one of those ripples to make it out to a point, that is going to give you your frequency. Then if you're going to
Just
measure...
how many ripples per second
exactly
go by.
And then if you're going to measure the distance between two of the ripple peaks, that is giving you the wavelength. So it's giving you two really important characteristics to understand: is this low energy? Is this high energy? Are we looking at X-ray light? Are we looking at infrared?
So all that distinguishes X-rays from infrared is just the wavelength of the light.
Right. They're all just forms of energy.
All right. And so give me the full list of all the electromagnetic spectrum.
Starting with the coolest, we've got the radio, and it is typically associated with temperature as well. So you've got the coolest material that is sort of the longest, and then you've got the hottest material, which is typically going to be sort of like really high. And so you've got the radio, you've got the microwave, you've got the infrared, then you've got our tiny little puny visible, itsy bitsy, right?
Red, orange, yellow, green, blue, violet.
And then you're going to go on to the ultraviolet, and then to the X-ray, and then to the gamma rays. So it's this beautiful expanse, and having all these different kinds of light, it's like having different tools in your tool belt to pull out at any time. So you want to use the appropriate tool. You don't want to use a hammer to screw something in, right? You want to use the appropriate tool. So if you're going to try to look for an exploded star in the aftermath, you want to use X-ray light. If you want to look
Because
through...
you know in advance that's a high X-ray,
energy phenomenon.
High energy phenomenon.
Exactly.
It's going to give you high energy light.
Exactly. Or if you want to look through to like ancient galaxies, you want the infrared light with a James Webb Space Telescope.
Wait, but that's a special case.
It is a special case.
Okay, because those galaxies were not given off, they're brand new galaxies, they're not giving us infrared, but you're watching them in infrared.
Right.
So what happened in between?
Well, the universe is expanding and things are stretching out. So it kind of changes everything, unfortunately.
Yeah, so one of the most brilliant features of James Webb is we want to look at early universe galaxies being born. And the birth of galaxies is rich in all your favorite high energy.
Yes.
Except since then, the universe has expanded, the light in the universe got stretched, and it's no longer ultraviolet or X-rays. It's been red shifted in so far past the visible light into the infrared. So you tune James Webb for the infrared, you get to watch galaxies when they were emitting ultraviolet.
Even though they're not actually in the infrared, the universe itself as a medium that they're riding on stretched it out. Like if that was the car, you turned it into a stretched limo, and now it's infrared, and now you can see it.
And you can go a step further and you can actually use these different kinds of light together. So for example, a recent headline was that the James Webb Space Telescope and the Chandra X-ray Observatory worked together to find the most farthest black hole using X-ray light and infrared light. So they found the galaxy with that infrared light, and then they looked for like the imprint of the X-ray from Chandra. And so together, using an older tool and a newer tool and time, they were able to find the earliest black hole, like 13.3 billion
So it's a
years.
fortunate coincidence that the infrared part of the spectrum, tuned to see the birth of galaxies, is just the kind of light to see into nearby gas clouds to look for stars being born.
Exactly.
If
Pretty
you
amazing.
can combine the infrared with the X-ray and gamma, will you find Marvel superheroes?
I think so. You'll definitely find the Hulk, if nothing else. I don't know if anyone operates an X-ray besides Superman.
Well, there's
That's DC, right? Non-Marvel. So.
Superman's
All
DC,
right. All right.
correct.
Gotta be
forgive
careful.
you. I saw where
Gotta
you were
be
going.
careful.
I didn't want to be that guy.
I know.
Yeah.
You're on notice now, in case
I know.
you don't get that Marvel or DC universe right. So I'm reminded of one of the characters in Star Trek: The Next Generation, Geordi LaForge. There's the character's name, played by
LeVar Burton.
Kunta Kinte. Yes,
Yeah.
LeVar Burton.
Oh, I'm sure he'd be very happy to hear that.
From Roots back in the 1970s. He was Kunta Kinte. Dude, if you look on his Facebook page, there's a picture of him as Kunta Kinte. So he
It was a long time
remembers the
ago,
role. Okay.
I'm sorry. I'm just sure, like, LeVar Burton, who's done everything in show business, and somebody walks in, like, Kunta!
All right. His character had lost his vision.
Yeah.
And they outfitted him with a visor, which is in fact an acronym, VISOR, visual instrument and sensory organ replacement. So this enabled him, previously blind, to see every band of the electromagnetic spectrum.
It must have been chaos.
Well, that's what I'm wondering.
I mean, that's too much.
They're saying
It's
this
too
is
much.
good. And I'm thinking, do you really want to see it all? You all would be glowing in infrared because you have body heat. I'd be seeing your cell phones lit up from microwaves.
Yeah.
I'd see radio waves coming through. It would be a mess.
I gotta tell you, it sounds pretty doggone cool to me.
I don't know.
Maybe it's
too
me.
much.
but,
Too
yeah.
much information.
But again, I'm the only one up here who smokes marijuana.
So he was clever. So the writers were clever to have that as a character
It was
in
cool.
the show, and I think he had the ability to sort of tune.
Oh, did like
You know,
things
he
out.
could select what he
I
wanted.
think he could
all
select.
right.
It
That's
wasn't a
much better.
cacophony.
Okay.
He could
That's all I could picture.
Yeah.
That's-
So in episode 213, he actually...
Don't be lying. No,
No, but it was very believable, wasn't it?
It was.
It was.
Just for a minute. I said, no, you do not know what episode 213 was. There weren't that many episodes of that show.
You're absolutely correct.
So if JWST can see the birth of galaxies and see the birth of stars, which means the birth of planets made of ingredients of life, it gives us access to stardust, out of which we are all made.
Oh.
So tell us about the Chandra Telescope and what it was designed to do and why.
Sure.
And
Well,
who's it named after, first of all?
so it was actually named after a brilliant Nobel-winning prize astronomer or astrophysicist, an Indian American named Subramanian Chandrasekhar. And what I love about that, actually, the naming was a little contest that NASA had held. And
They do that for almost
they
for
do.
many of their
Yes, they do
missions.
for a lot. Students wrote in, we had teachers write in, and the winning entry was for Subramanian. And the two winners, a student and a teacher, separate, by the way, not together, both went on to become astronomers, which I actually really love the sort of symmetry of that. But so anyway, so Chandra gets to look at the high energy universe. It gets to look at things like exploding stars. It gets to look at things like galaxies. It gets to look at things like clusters of galaxies. Black
So
holes.
just to reaffirm, those things involve high energy phenomena.
Yes.
And X-rays are high energy light.
Right.
And like you said about the chair, occasionally matter barfs up a photon.
Right.
If the matter is high energy, it's going to barf up a high energy photon.
Yes, exactly.
Is the universe really just that simple?
Barfing up photons? I think so. I mean, I feel like that could be a book.
Okay.
Or
Yeah,
something.
I guess so.
You should write it.
No.
People will buy that,
Really?
especially young people. I'm
Yeah.
telling you right now, barfing up photons. I want to go get it right now.
Yeah, that's pretty good. That's pretty good.
Okay, so in AD 1054,
Yeah.
on July 4th, the universe celebrated American independence with a star that exploded.
Yeah.
It was recorded by the Chinese.
Yes.
And today we observe that object on the sky as the Crab Nebula.
Yeah.
Named just because it looked very crabby.
Yep.
We have only seen it with regular telescope, and then you come along and put an X-ray telescope on it, And what did you find?
So the Crab Nebula is this beautiful example of what happens when a really massive star who starts running out of fuel, it collapses essentially on itself, and then it just explodes its guts out into the universe. Now what happens with the Crab is that a neutron star formed, and a neutron star is like this super dense, like a teaspoon of the material probably weighs more than all of the people on the planet, right? It's super dense, and it's creating these beautiful rings and jet-like structures because there's this antimatter and matter kind of collision stuff going on. And then you're seeing essentially the results of that. Chandra is actually able...
Well, you just said that casually.
I know.
Matter, antimatter.
Yeah, she actually sounded like she was on Star Trek for a second. Like it made no difference. Yes,
I feel like that's going more to the Marvel universe, right? Isn't there something like that?
Yeah, just to be clear, just tell everybody what antimatter is, just to put it on the same page.
It's just this particle that essentially, I mean, you explain it, I guess.
Okay, yeah, I could. I mean, it's matter has an antimatter counterpart. It was predicted and then discovered in the last 100 years, by the way. People alive today were alive before we knew about antimatter. So it's a real thing before it became a science fiction favorite source of fuel. And every particle has an antimatter counterpart. And the universe creates antimatter routinely. It happens in the center of the sun, happens in our particle accelerators. In the film Angels and Demons.
Oh, I liked that one.
Yeah, the Dan Brown second novel of that series. It reports that the Catholic Church had isolated a vial of antimatter.
Oh, that Pope.
And it's
totally
walking
forgot about
around the
that.
Vatican with this vial of antimatter.
If anybody can do it, it's the Pope.
And it's looking at like it's some cherished thing that nobody else in the world has.
Yeah.
And it's like, dude, we do this in the lab all the time.
Yeah.
So, no, this is not a special
I totally
moment.
forgot about that.
I saw that scene. I was like, nah, I don't know.
So why is it? Why they call it antimatter?
Oh,
is
because
it like
you bring it together,
right?
They both annihilate, and then there's no matter left at all, and you just have pure
energy?
Wow. Yeah. And so that's high energy. When antimatter, you're getting X-rays, gamma, you're getting all high energy there. So that's in your list of things going on
in the Crab.
The Crab.
Is that the Crab Nebula?
That's the Crab Nebula. And
No,
you can
excuse
actually,
me, with all due respect.
It doesn't look like a crab.
Where is the crab?
I know. So I think it was because in optical images, if you look at this object in visible light, maybe has a crab-like structure.
Okay.
I'll be honest, I still don't see it, but that's where it came from.
Because I'm going to say if that's kind of like the constellations, like you look at the constellations and let's be honest, like you're like, were these people high? Because
I don't see a bear.
I don't see a bear. I don't see a crab. I don't see a guy with a bow and arrow.
Yeah.
3 of the 88 constellations just barely resemble what they're supposed to. The rest requires high imagination.
What are the 3?
Orion is good.
Yes, Orion's
Okay.
pretty good.
Because that's hard, imagining a belt. Okay.
Yeah.
Okay. Leo the lion is a good lion. Yeah, I'll give him a lion.
Yeah.
Okay.
The
No, Big Dipper's not a constellation.
No, that's an asterism.
It's an asterism.
But I liked the audience participation there.
In fact,
By the way, don't act like y'all didn't think the Big Dipper was what she thought it was. Everybody's up here just like, oh yeah, look at that, Neil got her good, didn't they? Doggone well, you thought it was a constellation too.
okay. The point is, an asterism, like Kim said, is a more interesting subset of all the stars that make up the constellation. It looks like a dipper, yes, but that's not the name of the constellation. It's the Big Bear, and the handle of the dipper is a big bushy tail of the bear, but bears don't have tails, okay? So, okay.
Maybe the bear was cooking and had a ladle. It's just
Maybe.
Bear cooking with the pot.
right.
I see.
Yeah,
I see.
See what I'm saying?
You could have drawn the bear differently so that it would be using a utensil in a kitchen. Yes. But that's not how the ancients thought of it. All right. Back to X-rays.
Yes. More importantly.
So we're going down the list of what will trigger a detection in Chandra. So high energy collisions, you have a pulsar, neutron star. That is very dense. Keep going on that list.
All right, so then we get to things like clusters of galaxies, for example. Yep, there's one right there. One of the Abels. Beautiful. What Chandra's really good at detecting in this case is A cluster of galaxies is essentially tens, if not hundreds, and sometimes even thousands of galaxies bound together. But what makes it cool for Chandra, or I should say hot, what makes it hot for Chandra is that there is all of this like a bath of hot gas that envelops the cluster. So you can see that hot gas is colored blue in this image behind us.
So that gas is not part of any one galaxy.
Right.
So it's seeing the immersed bath is the
Bath.
word.
That's all I can think of is
It's a
bath.
gas bath for
It's
all
a
the
gas
galaxies?
bath. Yes,
It's a gas
exactly.
bath.
A
Yeah.
galaxy gas
Yeah.
bath.
Yeah.
Okay.
That's pretty cool.
Yeah.
All right.
Chandra gets to look at more than just that. Like, it is amazing because, even though Chandra was built in the 90s essentially and launched just around the time that we were starting to understand what exoplanets were, Chandra gets to look at exoplanets. Chandra gets to work with the James Webb Space Telescope a lot, looking at things like star formation, because stars, when they're first born, they're cranky. They're like cranky toddlers, right? So they can emit like these flares, these X-ray flares. And what's useful about that is if it's a very cranky star and there is an exoplanet being born nearby, how cranky that star is will have an impact on the possible habitability of that planet. So it's very useful to understand like what the star's tantromeres were like.
Okay, so you just said something that has a built-in fact that I want to make sure everybody's clear on. Why would the high energy X-rays have anything to do with the possibility of life on an exoplanet?
Because of the flares from that star, those are the high energy X-rays, right? And X-ray light going towards a young planet that perhaps does not have a super protective cover like Earth does with its atmosphere can do incredible damage. And even if it does have an atmosphere, if it's powerful enough, those X-ray flares can still do a lot of impact in a negative way to any life that could potentially form as we understand it.
So the molecules that are the foundations of life do not do well in the presence of X-rays.
All that radiation, not so great.
Okay, so I first realized this getting X-rays at the dentist.
Yes.
And I always wondered, why do they go outside the room, close the door, and then they flick the switch? Why is the switch out there?
Yeah.
Like, why isn't it right next to me?
Because they're doing it 10 times a day.
Still, I just said, there's something going on in here that did not go. So, yes.
So Neil told him, could you just sketch my teeth?
Yeah. Don't look inside.
don't need to. So I want to hear more about what Chandra can detect, especially in the realm of black holes. But I want to first hear you explore what are the challenges of making an X-ray telescope? Because a regular optical visible light telescope, there's a lens or there's a mirror and it focuses light. We have magnifying glasses, we have microscopes. There's some familiarity that we have with those items in our culture. But X-rays is a whole nother.
Yes.
So what's going on there?
All right. So X-rays are really interesting because they're so energetic. You can't have just a normal flat mirror like you could for Hubble, for example, because X-rays will essentially just absorb. It's kind of like if you fire a bullet at a wall, it'll just boom into the wall, right? But like if you have a gun expertise, if you fire it at an angle, right, you can have what's called a grazing angle and it can ricochet off. So the same thing with X-rays, you have to essentially create these really nested barrel-shaped mirrors that can just kind of graze the X-rays down a very long distance to the very sensitive detectors at the end, because otherwise you just can't capture them. But in order to do that, your mirrors, they have to be not only this interesting barrel shape to kind of skim,
Multiple mirrors in a row.
Multiple,
As
four.
you graze
Yep.
each one.
and they have to be incredibly smooth, like down to at the atomic level. Like if you took Colorado and sanded it down, Pikes Peak would be like less than an inch tall. Like it's a truly like smooth process. And to be honest, I think they might still be the most smooth mirrors ever produced to this day.
Well, I've still got to get through your Colorado.
Okay,
analogy.
Colorado.
Wait. So
Pikes Peak.
you're saying if Colorado,
Took the whole state, just smoothed it right down.
which has Rockies going right
Yeah.
through it,
Yeah.
if you made Colorado as smooth as the mirrors
On Chandra.
of Chandra,
Pikes Peak, less than an inch.
Pikes Peak 1 inch above
Yep.
the surface of the state of Colorado.
Yep. And they also have to be super clean, by the way. So if you take like the size
There
of
goes New York.
Yeah, I could see that. So if you take something like the size of a computer monitor, you could only have one teeny tiny speck of dust on that entire size. So they had to be very clean. And then they had to be coated with iridium to make sure like that X-ray light could be focused down.
Iridium's very dense metal.
Very dense. Yep.
Because you don't want the X-rays busting into it.
Exactly. Like bullets into a wall. You don't want that. So you have to create this very smooth process for the X-rays to go down 30 feet to the sensitive detectors.
Wait a minute, 30 feet. So
30 feet.
This is in a spaceborne telescope.
Yeah, and
how'd you get it up there?
It's about the size of a school bus. So we packed it in really tight into the space shuttle and hope for the best and sent it up.
What do you pack it in tight? It's like luggage?
No, it was literally... There was no
squeeze your
room
underwear
to
in.
spare.
You missed
None.
the best part of that statement.
What?
It was?
And we hoped for the best.
Well, I mean, I hope for the best. I was young.
The shuttle was not a suitcase.
No, but it was kind of being treated as one. Like, it barely fit in there. And I don't know,
But it was
like...
designed to use all the available volume.
Yes, like 100%. And it actually made the flight for the astronauts that were bringing it up risky, because if you have a very heavy payload, your abort scenarios actually become less positive. I don't know how to say that well. Less like, I don't want to say less likely, but
Yeah.
you know what I mean?
We know they're screwed.
Yeah. Yeah. So if
basically it.
Chandra if they had a problem with launch and Chandra was still on board and they had to come back, it would have been very, very challenging. Very challenging.
But you just drop it in the Atlantic. I mean,
No, because they wouldn't have had time to just empty it out.
can't empty
It's
it?
also, it goes out with the arm. Like, so it's not loosey-goosey in there. You know what I mean? It's not like a pair of glasses rattling around in your suitcase. So yeah.
Yeah, they're screwed.
Yeah.
Yeah.
okay.
Yeah.
But it worked.
But it worked
Yeah,
amazingly.
beautiful.
It worked perfect.
A shout out to the engineers
Yes.
that work closely with the scientists
Yes.
to make all this work.
Yep. And mission
it's not the
control,
scientists
everybody.
inventing that.
No. But like everyone, the astronauts, the mission controllers, everyone, like they were just on point. Yeah.
Give me a couple
By
more
the way, I'm
examples.
sorry. I believe this requires a USA.
Oh, yeah. It is a good one.
USA.
Well, I like
The
that.
Olympics are over.
I
okay?
know, but it's okay.
Not the
Well,
Olympics of space, baby. We are still gold medal.
I mean, if we could take a moment of national pride, X-ray astronomy was created in the U.S. and like we have this incredible expertise that to this day, like Chandra is still the most high resolution X-ray detector that we have. And it's impressive.
And that's from the 1990s. So
Yes.
we're talking 30 years.
Yes, it's been 25 years that it was launched just last month. Wow. Yeah.
Well,
Yeah.
excellent.
I know.
God, I love
Anyways.
this country.
So you are working at the Center for Astrophysics
Yep.
up in Cambridge, which is the joint title of the Harvard College Observatory and the Smithsonian government, Smithsonian
Yeah.
Astrophysical Observatory. I remember being there, because I'm that old, in the 70s,
Yeah.
where X-ray astronomy was being born.
Yes. Yes.
And the earliest X-ray detectors, they didn't have good resolution. We just wanted to detect whatever was up there.
Yeah.
And I remembered the challenge that it put upon the design engineers because the payload couldn't be very big or heavy. And so the earliest X-ray telescopes were these miniaturized X-ray detectors. Right around that time, the U.S. Congress says, we want to scan everybody walking into the airport to not have weapons. Well, how are you going to do that? X-ray detectors. Did they have a portable X-ray? No, they came to the astronomers. You've got one? Yes, we did. So my people in the day pioneered the X-ray technology that first landed in every airport in the United States.
Yeah.
In the 1970s.
Right.
A whole company was created for that, American Science and Engineering, which had Riccardo Giacconi.
Yep. Who won the Nobel Prize?
He won the Nobel Prize for
X-ray
his
astronomy.
whole effort in X-ray.
Yep.
So the correspondence between moving frontier of engineering and astrophysics and applications on Earth has a fascinating backstory there, but it keeps going to modern time.
100%.
Give me some more examples.
Yeah. So, like I mentioned, Chandra was really challenging technologically to build. And so technology had to be invented just to create Chandra. And so what that means is like when today, because we have so many clever people that know how to recycle these technologies and create these spin-offs, right? So today when I'm getting a mammogram, like that technology has been made more high resolution and lower dose because of Chandra. An MRI.
So mammograms are x-rays.
X-rays,
Yeah,
yep. When I'm doing an MRI, for example, the low dose of those magnets that they use, that's because of Chandra. Environmental monitoring of like shark populations has been improved because of X-ray astronomy.
Sharks?
Yes. Environmental
What does
marine.
that have to do with x-rays?
Because the way you monitor them from, I'm not an oceanologist or sharkologist. I don't know what that word is, but you know
Because neither of those words exist.
I know,
That's why,
it's okay.
that's why we know you're neither of
we
us.
can make it up. We're all friends here.
Oceanologist.
And listen, I believe I actually tried to pick up someone at a bar once and told them that I was an
I am
oceanologist.
clearly not working in marine affairs.
Okay.
But Chandra technology is being used to study those populations of things like shark in the ocean.
So there could be sort of algorithmic tools and tactics
Yeah.
that are needed for the astronomy that then have applications.
Right. That's definitely part of it. I mean, it's like when you do really hard things up there, like to get up there, like you get to improve things down here. And that's really cool.
Yeah.
So I know that it gave us airport x-rays, but is it possible that Chandra could fix the TSA?
No. That's asking too much for Chandra. Chandra's got a lot of black holes to look at. So got work to do.
We left off with pulsars, neutron stars, as high energy places.
Yep.
Let's keep going. So-
Okay. Black holes.
Black
We
holes.
talked about that. So Chandra actually became a black hole hunter. What's really interesting is the actual scientific point of Chandra at first was because when X-ray astronomers looked up into the sky, there was just like a sea of X-rays everywhere. And so Chandra was created to resolve that, what was called the X-ray background. And it was one of the first things Chandra did, and it found that it wasn't just a sea at all because Chandra brought into sharp focus and found that it was mostly black holes.
So the early detectors just couldn't, just some x-rays coming from out there somewhere.
It's like taking your glasses off. You just see a haze. Well, I have very bad vision. So when I take my contacts out, that's what Chandra was able
so
to
if
do.
you take your glasses off and it's a blur, you would just think there's just a blur of light.
Right.
Now you boost the resolution and you say, well, there's a source of light there.
Exactly.
And right there. So Chandra,
Chandra found that there were billions and billions of black holes.
black holes.
Black holes?
Each one of these.
Mostly were black holes. There was other stuff too, of course.
But wait a
but it's
minute,
black
if a
holes.
black hole, if no light escapes a black
yeah.
hole,
Yeah.
what are you actually seeing then to know that it's a black hole?
Yeah.
It's a great question.
They'll just try to
I
slip
need
black
some
holes
help
by
over
us.
here. Yeah.
Okay.
So this is actually Centaurus A. This is a very active galaxy, and that very bright white spot at the very center, that is essentially the area that the black hole is. You'd have to zoom in super, super deep to actually find the black hole, but that's where it is. Now, this is an active black hole, which means we've also got jets of this high energy material streaming out as well past that like dusty disk of the center area, right? So that black hole at the center is powering all of that like amazing energy that you're seeing. So back to the question of like, how do we see them if we can't see black holes? Well, so black holes, are kind of sitting there doing their thing, but they have a lot going on because they're in an ecosystem, right? So if there is stuff around that black hole might need to have a snack. If it's an asteroid nearby and that kind of falls into its gravitational pull, there might be a little small X-ray flare. If there's like a big massive star being chomped on by that black hole, now you're going to get a much bigger X-ray flare. And those burps can cause all sorts of cool things that Chandra can see.
And it's fed by a disk.
Yep.
An accretion disk.
Exactly.
We call it. I have an accretion disk myself. Middle-aged man, accretion disk. Where matter gathers
Yeah.
and spirals down toilet bowl style. But that's a place. That's the ecosystem I guess you're talking
Right,
about.
right.
And because as more matter, if there's matter available to be consumed, it's got to confront the accretion disk before it gets into the black hole itself.
Exactly.
And you're saying that's where all the action is.
That is where the action is. Like that's the downtown. Some of you have probably seen like the first images of a black hole from the Event Horizon Telescope, for example. I mean, I never thought I would see that in my lifetime. I'll be honest. That was just amazing. So it gets to see the silhouette of that, right? That you were just describing. It's seeing the shadow of that black hole. What Chandra sees is further out because every black hole sits in an environment. It's not in a vacuum, right? So we've got all this stuff around it, and that stuff kind of tells the story of how the black hole is acting, what it is doing, what it is eating, if it's sleeping. Like our own black hole right now is kind of sleepy. They call it a sleeping giant.
The one in our own Milky Way.
In our own Milky Way.
Because every big galaxy's got its own black hole.
Exactly.
Yeah.
Right. So ours is kind of sleepy, which is what they say. I'll take their word for it. Which means
Sleepy black hole.
which means we're in a good place though, right? So we don't have a whole lot going on with our supermassive black hole. That's cool. But in something like Centaurus A, it's awake, it is super powered, and it is blasting out an intense amount of energy because there's a lot happening in it.
All right. So even though everything wants to get in a black hole, it's got to work its way there.
Yep.
And not everything makes its way in.
Right.
Because there's so much activity there. There's some actions that actually spew matter back out.
Right.
And it's not coming out of the black hole itself.
Right.
It's coming out of the ecosystem.
Energy
Exactly.
around it.
Around it.
Exactly.
Okay.
Yep.
That's very cool.
Isn't that cool?
Okay, so now I understand that you can also detect dark matter.
Yeah. So dark matter is fascinating, right? One of the things I love about astronomy is like it's so humbling. Like we know nothing. We know nothing. And so if you think of the universe as like a jelly bean jar, 95% of those jelly beans are going to be black because they're representing either dark matter or dark energy, right?
Very unpopular jar.
Right? So dark matter is sort of like the thing that holds things together, and dark energy is something that's like pushing things apart. That's kind of how I like to think of them. There's only 5% of those jelly beans are going to be colored like normal stuff jelly beans, like the ones that you want to eat. I don't like the black licorice ones. So like the cherry ones, the whatever the white is, coconut, I don't even know. 5%, that's it. Most of the universe is dark. And so it was really interesting because when Chandra started looking at these clusters of galaxies, right, these bays of hot gas, if you will. One of them in particular, I'm forgetting its scientific name, Able something, but nicknamed the bullet cluster, clearly showed that the normal matter was essentially being dragged behind the dark matter, or I should say like the gravitational information that we were getting of the dark
You're
matter.
describing the bullet cluster.
The bullet cluster.
But you're not directly detecting the dark matter.
You're not, because it's invisible, but you can essentially map it through the pull. The gravitational lensing will give you, it's like if you use a wine glass to like look at light, it kind of bends. So with that bending of light, you can use it as a tool to map things. So like the pink stuff is the normal matter. That's the baryonic matter. That's all like the stuff that we're made of, for example. The blue stuff is just a map of the dark matter. And now dark matter doesn't really interact with stuff in the way that normal matter does. So you can see that the blue, and this is a collision of two very massive clusters of galaxies. This was, at least at the time, the most energetic event that we had in the universe after the Big Bang. And so the blue matter, you can see, is ahead because during that collision, the normal matter, it's like air resistance, and there's a drag on something. And so you can see that it kind of stayed behind, but there's no such problem for the dark matter. It doesn't interact like that, so it just keeps going.
And so the lensing, I mean, there's a huge history behind lensing.
Oh, yeah.
Where Albert Einstein predicts that intense gravitational fields, which dark matter would have,
Right.
would distort images of galaxies in the background, and then you'd see this effect, almost like a funhouse mirror. So that would be the evidence that there's still a lot of gravity there, even if all your matter was left behind.
Right, exactly.
So it just ripped the two apart.
Right. So this was a technique that kind of showed it work. So this was the first direct proof for that. And they've then applied that to like dozens and dozens of clusters of galaxies since and saw the same thing.
So just to make sure we're on the same page, we are on a planet around a star. Our star is joined 100 billion other stars in the Milky Way. And there's 100 billion other Milky Ways out there, but they're not all evenly scattered. If we look out there, we find that many of them are clustered. So clusters of galaxies, not just clusters of stars within a galaxy, clusters of galaxies. And you just described two clusters of galaxies that collided.
Yep.
Passed through each other.
Yep.
The dark matter kept going. The regular matter got left behind.
Exactly. Isn't that neat?
That's crazy.
It is crazy.
That's crazy.
Yeah.
Crazy. So now that we all have a cosmic vocabulary,
Yeah.
now you're going to take us away from that because you've been showing us pictures until now. But that's not even your specialty. Your specialty is what else do you do with those pictures?
Yeah.
And it's data sonification.
Yeah.
What motivated you to convert visual images into sound?
So I love data. Like I'm just a data junkie, right? And so I'm always trying to figure out if a scientist is going to be working on a problem, like what kind of ways do they need their data in order to figure it out? What might be new ways that'll offer us like new avenues of opportunity? And then conversely, I'm also thinking, and what do people like want to experience with this data? Well, a friend of mine, Wanda Diaz, she's an astronomer and a computer scientist. She's been blind since she was a teenager. And she talks about how when she was in school, a professor would be writing on a blackboard and she couldn't see it, right? Like a math equation or something. And so later on, she went on to develop technology to essentially take data and translate into sound. That's the process of data sonification. And she uses that to study stars, to understand stellar characteristics. And I have another friend, Gary Foran, who is an astronomer who does the same thing. He uses sonification to be able to study galaxies, for example. So our goal was to take the data that we had been creating from Chandra and from other telescopes as well, and just mathematically map that into something that you could hear to see like what would happen. It was especially over the pandemic, so we had a little more time to like play. Do you know what I mean? Like, well, we weren't doing events. We weren't doing a whole lot. Like, there was just so much that had changed.
You were bored.
I wouldn't say that. Never bored. But we had time to think a little differently.
No, we get it.
And sonification was just, I don't know. I loved the way it came out.
It sounds like the data sonification not only serve those who are vision impaired, it might offer other elements of interpretation for the data, even for those who are sighted.
Yes, it's like another tool to have in your tool belt, right? Particularly if you think of different kinds of objects, like a variable star is a star that's like changing frequently enough that humans can map it. And we get a lot of data on these variable stars. But the human sense of sight, if you're just looking at a chart of that data changing over time, it's a little bit challenging. The human sense of hearing is really good to be able to pick out some of those variations, right? And you can also train to become a better listener of your data. There's been research to show that. So it's not only a tool for scientists, it's also a way of understanding it if you're blind or low vision. And it's just been a joy of a project to work on. Like,
So when I think of data sonification, there are a lot of different, should I call them dimensions that you can cue on. So there's the color, which would be like the frequency, the wavelength of light. There's also the intensity.
Yep.
Right? It's a whole other thing.
Yes.
That's not even the same as the color. It's just, is it bright or is it dim?
Yep.
Right? And then there's location on an image. These are all sort of separately trackable bits of data, and you have access to all of these.
Right. Right.
And you decide what would best serve the need of the moment.
Right, because you have the scientific story that's embedded in that data, and you're trying to essentially communicate it. So you try to figure out, all right, the best way to communicate this exploded star through sound is through a radial mapping, because you're going to trace essentially the shape of that exploded star.
We have Cas A.
Yes.
Was that an example?
Yes.
Okay,
That's
so
perfect.
tell us about Cas A.
Yeah, so Cas A is an exploded star. It's the leftover debris field from that star that exploded its guts out all over the universe.
Oh, just want to say, Cas A is short for Cassiopeia. A constellation, who's the queen of Ethiopia or Egypt, some African country, Cassiopeia. And if you wanted to find her, it's just a big W in the sky.
Yes,
That would
I
be
actually love that
an
one.
asterism.
Yeah.
A W.
'Cause it
But
looks
otherwise
like a
it's
crown.
a throne. Right. Okay.
Yeah.
So and we just named because we find that object within the stars that track that constellation.
Exactly.
With an
So
A.
it was the first. It was
the
A.
first A. There
Exactly.
it is. Okay, so
Yeah.
pick it up.
So Chandra has looked at this object many, many times. So has the Hubble Space Telescope, and recently the James Webb Telescope have as well. And you can see, like, it looks electric, right? So you're looking at the color coding of this object is actually telling you about the chemical composition of it. So we're able to detect with Chandra because it not only has two detectors, it also has like gratings that can essentially capture the fingerprint of light, that DNA.
This is just Chandra.
This is just Chandra.
And how long is this exposure, if you will?
About 2 million seconds.
Okay.
I know.
Yeah.
There's not as many X-ray photons in the universe, right? And so you do have to look at them.
You gotta wait around
You got to
for them,
wait
that's
around
right.
for them. You got to be patient.
So I could
And do you guys ever?
just apply I need 2 million seconds worth of observing time.
I was going to say,
Well,
do you ever
this
speak
was-
in terms of hours and minutes?
So this is actually interesting target for Chandra because it's in such a great spot of the sky. Chandra can look at it over and over. So it's called a calibration target because we can use it to make sure everything on board the telescope is working beautifully. So it's not only the time that scientists have proposed for, but we also have more time because we check it for like engineering issues as well.
Oh, so I just got to clarify there. Cassiopeia is what's called a circumpolar constellation. So it's closer to the North Star. When you're orbiting the Earth, half the sky you can't see because Earth is in the way. But some of those stars that are near the poles, you get to see for much longer periods of time.
Yeah.
And when you said it's almost in continuous view, that would be why.
It's in a great view for Chandra. I mean, Chandra does go about a third of the way to the moon, but there is still lots of stuff in the way, right? And you still have to worry about all sorts of things. So it's in a great spot for Chandra to be able to view over and over again.
Okay,
So we
so-
get this deep view.
Okay, so now what are we about to experience here?
All right, so we're going to listen. So I mentioned the chemical elements, right? So there's iron in here. That's like the purple. There's silicon, there's sulfur, there's calcium. All of these different elements have been mapped with color. So instead of just looking at it as a visual, we're going to hear those mapped to sound. And so the lowest is iron. You'll hear it as we sketch radially from the center where that neutron star is, the leftover core of that star that exploded. And as we go out kind of tracing the expansion of that debris field, we'll hear it as we start to go through the iron, the silicon, the calcium, the sulfur, all the way out to the very bright blue rim, which is essentially a very bright like shock from as it sweeps up into that material
And what's
around
the
it.
blue rim made of?
It's very electric. It's electrons. It's all of that.
Okay, so it's not one of those elements
Nope,
specifically.
it is just the highest energy shock from that material.
Okay, so this was a supernova.
Yep.
Do we know when this supernova went off?
So I think it was about 400 years ago, but it's like 11,000 light years away. So, how old it is relevant
Right.
to Earth time or space time.
Right.
But yeah.
So it actually happened 11,000 years ago.
Yeah.
While we're just coming out of
We're
caves.
just, yeah.
Okay.
Yeah.
We're just inventing agriculture.
Yeah.
But we saw it.
We saw it.
Before
Well, there might be tracings of seeing it. It's kind of one of those unclear ones, but yeah, about 400 years
Okay,
ago.
so let's check out.
Yeah.
Okay.
Let's listen.
Okay, this sounded like the Philharmonic just warming up.
Tuning up, right?
Just tuning
Yeah.
just before they
Yeah.
begin.
And that was an exploding star.
Yeah, the debris field left over when it barfed its guts out all over the place.
I would have thought more like,
Well, we're only hearing the leftover part. So
The leftover.
and it was really important to communicate. So the iron, for example, that was like the lowest note that you're hearing. What's cool about this explosion is that right before it exploded, the iron would have been at its core, right, as the heaviest element that it could produce before the explosion. After the explosion, it's more along the perimeter. That tells you that this star actually turned itself inside out when it exploded, which is very cool. And so as you're listening to it, if you have, the technique to listen well, you can hear it as that lower sound really picks up towards the perimeter.
And I'm just realizing now that you need to be trained to know how to listen to this
Yes.
sonification.
Exactly.
But that's not any different from being trained to learn how to look at an image.
Right, 100%.
You need an astronomer there to tell you, well, this is that, and this is that, and
Yep.
this is what happened there.
Yep. We provide captions to kind of help that, but yeah. And we also separate out each piece so you can hear it individually so that you can actually learn to listen yourself. But yeah.
Got it. So you got another one? How about
Yeah.
the Carina Nebula?
Yes.
This is one of my favorite JWST
It's
images.
stunning.
You can't argue with
No,
this
I
one.
can't.
Because what's going to happen here?
So in this one, we're listening to this beautiful area of star formation. It's called the cosmic cliffs because you can see all of that really cool gas and dust down there towards the bottom that the James Webb picked up. And then you're seeing all of these young stars that have been recently birthed and are starting to mature and stuff. This one was broken down a little differently because the actual star formation area towards the bottom is so distinct from the visual of just the kind of empty space, if you will, just stars up on the top. And so it's divided into two pieces, and you'll hear the difference between the top and the bottom. All the stars are sort of like a clickety-clackety piano. Let's play it and see if
Okay,
that
let's go.
description makes any
There you go.
sense.
That was beautiful.
Yeah, and I should say, I don't think I've mentioned it. We actually work with people who are blind or low vision to create these because that really is that first desired targeted audience. And then other people obviously enjoy them as well. But we wanted to make sure, as somebody who has to listen to the world around them, that it made sense to people who are blind or low vision.
Well, otherwise, what are you doing?
Right.
Go home.
Right, exactly.
Right.
Go home.
Did you guys ever think about starting a radio station?
That would be really cool. Just space.
So the gas clouds were telling us something different from the star points.
Right, exactly. You're getting that whoosh of all of the texture of the dust and the gas from that star formation area. And then you're hearing the individual stars picked out as, I don't know, clickety clackety. That's all I can think of to describe it. Sure, if there's a musician, you could find something better. But having that differentiation of understanding them is really helpful.
Now, one distinction, of course, is when you're sighted, you see the whole picture at once. Mm-hmm. But the audio track
gives you time.
Is a scan across it, either left to right in that case or center to edge.
I found that actually to be really important. I'm so glad you brought that up because I look, and I'm used to looking the most, right, as someone who's visual. And I have found that I have learned things about data I have been looking at for dozens of years because I'm listening to it over time. And it's, spoon feeding a slice of the image at a time. It gives me time to think about what else could be happening. And I've actually learned to digest it and to process it in a different way. And I love that that's a possibility.
Is this something that would improve if we closed our eyes?
Oh, yeah, I think so.
Let's do
as
this
an
again.
Activity, to maybe the next one, have them listen to that one.
Okay, what's the next one?
Maybe we should just listen to it first and then I describe it as something a little different.
Okay, so the next one is
V404 Cygni, I think.
V404 Cygni.
Yeah.
So V sounds like a variable star. Mm-hmm. Yeah. And this is a what?
This is actually a black hole, a stellar mass black hole, so one of the smaller ones. And it's got a companion star, and it's kind of pulling off some material from it. What that does is it causes these outbursts that then the light kind of bounces off of the gas and dust in the areas around it, causing light echoes. And you're seeing the light echoes as those rings in the X-ray light. But you're going to hear it, I think, more distinctly.
Should we close our eyes?
Yeah, let's close our eyes.
Let's do that.
That'll be fun. I feel like we're in a meditation class right now.
Yeah. So in that image, you just to emphasize, there are these places, these sort of concentric rings that are the emitted gas from explosive episodes in the past.
Yep.
That continue
burping.
to slowly move out. Mm-hmm. Then you have another explosive episode, but there's a gap between them.
Right.
And if you have another sort of episode, there'll be an energy wave that'll overtake those and then render them visible.
Right. And so it's kind of like, if you're driving in fog, your lights kind of scatter in that weird way. That's kind of what we're seeing. And so you're able to kind of trace the timing of this burping of this black hole in this way, which is really cool. But all that gas and dust that it's ricocheting off, that's kind of what that sound we were trying to mimic as you were hearing it. Almost sounds like ocean waves, which I feel like is very appropriate to the Hamptons.
Yes.
And how do you determine what sound to affix
I was going to ask that.
to the data?
Yeah, so it's a few things. So we have a whole team. I work with Matt Russo and Andrew Santaguida, who are both musicians. Matt is an astrophysicist. And we also work with Christine Malik, who is a consultant who is blind as well. And with the science-like story that we're putting together, we're trying to make sure it is as authentic as possible to the data, because it is a mathematical mapping of the data, like using Python into this process. And then you're essentially selecting
the programming language.
Yep, the programming language. And then you're selecting the sounds that will hopefully differentiate the objects the best and also describe the science the best, and in a pacing that lets you process the data at the best pace. So those are all things that we test for.
Wow. So it's not just you, rogue, in the back room.
Not a conductor. No.
Yeah, when
at all.
Dr. Dre had
No,
a booth.
I know. It'd be fun, though.
That would be. Yeah. Do you have any hip hop?
No, I don't yet, but maybe that'll change.
Yeah.
Hip hop and the
Think
universe.
about it. Never
Okay.
think about it. Right.
All right.
I mean, when you say black hole, there's got to be some hip hop somewhere in there.
And dark matter, dark energy.
Yeah, it fits. It fits.
Now, Hubble had a deep field.
Yes.
So did anyone do the crazy thing with Chandra?
Yeah.
To just look at in the middle of nowhere?
We did the crazy thing with Chandra. 40 days and 40 nights. We looked at this one patch. I know it is.
Oh my gosh.
We looked at this patch of the sky, and what we found was just a beautiful field of black holes. So it looks like you're looking at stars in this image. This is actually the deepest X-ray image we've ever captured. So this is really special. If you're trying to describe it, it's like someone just flecked like paint onto a black rectangle, right? It doesn't necessarily communicate the excitement of the science as like I think of it. Like this is the awesomest image ever. And so what we're going to do...
These dots on a page.
These dots on a page, because they're black holes. They are thousands of black holes. It was the highest concentration of black holes that we've
So
ever
if Hubble
captured.
had looked at this, because it can't see X-rays, this would just be filled with stars.
Right.
Or galaxies.
Or galaxies. Yeah,
Right.
Right.
And
But Chandra's detecting that high
It's
energy.
not seeing anything else there.
Right.
It's Geordie focusing in
Yeah.
on X-rays, and he sees
Yeah,
this.
black holes. Black holes everywhere. It was a black hole bonanza. Because the science was so exciting and the image to me never really expressed it. So this was an important one to sonify because I think it actually tells the story better. So we're going to listen to a scan from the bottom up to the top because it's actually in stereo. And each of these black holes is essentially color-coded by energy. That's a technique we often use in image processing. The lowest energy material will be color-coded to red and the highest energy material will be color-coded to blue with the medium in green. So kind
But
of
for
mimicking.
sound, how are you going to do it?
So it's the same thing. It's sound. So we've taken the red and coded it to the lowest note, and we've done the opposite.
Low
So
frequency, high
the
frequency.
blue is the highest, and so you'll hear that population of black holes, I think, in a very unique way.
Because just right here, we don't otherwise know. Just some are brighter than others.
Right.
But we don't know which has the highest frequency.
Right,
Okay.
right.
Let's check
All
it
right.
out.
Yo, that is my jam. That's the one.
That's my favorite.
That
I
is
love that
the
one.
one
It's
right
very
there.
cool. It's
Oh,
kind of
man.
vibey.
Yes.
Vibey.
Yeah. Oh, that's number one with a bullet, baby.
Yes. But like you just listen to a population of thousands of these supermassive black holes, like billions of light years away for the most part, right? And you've just heard that as you sweep through that field, which I think is pretty fun.
That was beautiful.
That is.
Oh, yeah.
It was very Pat Metheny.
It has this kind of like indie,
Thank you, Pat Metheny
indie
fans.
vibe to it.
There's only like 4 of you here. But I
It
know
makes
you
me
know
think
what
of
I was
Imogen
talking
Heat.
about.
That's who I think of. But yeah.
Those are some of the highlights of
Yeah.
what you've been doing.
Yeah.
Now, we talked about the bullet cluster,
Yep.
right?
On this one, we're going to scan from left to right. The X-rays, I believe, are like whooshy sound. I have to come up with better descriptors. I've just
you do.
realized. You'll hear the stars very distinctly, and then you'll hear a very strong kind of like note for the dark matter map. So yeah, let's run that one and see what you think. I mean, that was a whooshy sound. I don't know how else to describe it.
Dark
so-
matter didn't know what hit it. Isn't that right?
Right.
That one's very sci-fi.
It is a bit sci-fi.
Very sci-fi.
Yeah.
Very sci-fi.
It's no black hole deep field. I'm sorry.
I agree. That one is my favorite. Yeah.
So this is a tool to show us things we already know are there, right? So stars, galaxies, especially your high energy universe, which enchants you so. But there's any thinking about how you might detect dark energy, this mysterious pressure in the vacuum of space, forcing the universe to accelerate against the wishes of gravity. We know it's there, but we don't know how to represent it. There's also neutrinos, this ghost-like particle that moves through the universe unimpeded, very difficult to detect, but it's out there. This and perhaps other frontiers await your efforts.
Oh, thank you. I think, sonification is a very useful tool for that type of thing. I mean, I remember when the LIGO neutron star merger story had come out in 2017.
That detects gravitational waves moving through the universe.
And there's a very famous sonification that took the data and translated into sound, because for that reason that, you're not looking at an image of light in that case. So having to use some of these alternative tools to represent it, to analyze it, to me just makes sense. But I think there's a lot more we can do. Like, we've started working in haptification, which is using, for example, on your phones, if you've all got them on mute, like I'm sure you do, and you get a text, you'll get a little vibration, right? So that is the haptification.
So that's a haptic.
That is a haptic.
When there's a vibrational affirmation of something that just happened.
Exactly.
Okay.
And so we're just learning how to essentially harness that to be able to represent image data and other types of data as well. I don't know.
That's weird.
But
weird. I kind of like them because, for example, whether or not it's your phone telling you got a text message silently, but if you press a button and then you feel a little vibrational haptic, it's like, it
gives you the response. Yeah, exactly.
It's like, I just pressed that button.
Right. And that's the idea, right? So like using these other senses to be able to try to extrapolate out more from our data is something that I'm super excited about. Yeah.
And how about other ways of visualization, which are familiar to us all, whether or not we're embedded with them? So virtual reality.
Yes.
Or augmented reality is another variant here.
Any kind of mixed reality, for me, yes, exciting, because there are issues of like scale, right? And things like extended reality, mixed reality, augmented reality, whatever it might be that you're using.
Remind us what augmented reality is.
Augmented reality is when you've got like, say, a Snapchat filter on yourself, right? You're adding a layer of this reality to your own reality. Virtual reality is like a deeply immersive, you're only in that virtual reality. And there can be combinations as well. And so in astronomy, I can kind of picture in the not so distant future, one of my colleagues in Cambridge is doing some kind of data analysis on a black hole, and they're working with someone in Japan. And in real time, they're able to step through this object in virtual reality, or, pick your reality of choice, right? And they're able to use sonification to check the variability of that black hole, perhaps, whatever it might be. Like, there are all of these combinations of being able to process your data and to understand your data.
I always wanted movie theaters to do that.
Yes, so it'd be very cool.
Where the movie's just happening around you.
Yeah.
And you just walk up closer to the bar.
That is called life, Neil.
It is, I guess.
You're right.
Yeah.
Okay. I can't argue that. And what about 3D printing?
Yeah. Well, so
you've been a big 3D printer lately.
Yeah, I'm a very big fan of it. Yeah. So we have all these 3D models that we create for science, for scientific analysis, right? When you understand the red shift, the moving away of something from you versus the blue shift, what's coming towards you, you can map that into a 3D representation of this object. So then you can take that and you can move it to a 3D printer so that you can hold a version of it in your hand.
Wait, so just to be clear, until we figured out how to get the distance to anything, the sky was imagined to just be this sort of the inside surface of a spherical bowl,
right?
Which would make everything at the same distance. So
like
no one is
TV screen.
No one is thinking 3D about anything in the universe. And now that we have 3D information, you get to work on your 3D printing.
And you can represent it, 3D print it, hold a version in your hand, which is great. Again, if you're blind or low vision and you want tactile exploration of your data, it just gives you another avenue, and it's very exciting.
And so you just have people exploring this, be they sighted or not.
Yes.
It still has value
right.
in a 3D space.
Yeah, actually, Cassiopeia A was the first one that we'd ever done using observational data into a 3D model. So that was like super exciting for us. And we 3D printed it, and the response to it was so fantastic. So fantastic.
Well, excellent. We want to see where this continues to go. Is there a future? What is the future of X-ray astronomy.
Yes, so Chandra is 25, but still in amazing health because our engineers on the ground, like, it's too far to fix it. You can't, like, send up astronauts to fix it. So anything they have to do to take Chandra to the doctor is just through coding, right? Astronomy runs on coding, and they do a brilliant job with it.
And you just reprogram it.
You're just reprogramming it. You're doing little tiny fixes here and there. If, for example, you need to look at a different kind of object, you just reprogram it a bit, whether through Fortran or whether through C++, all of these additional languages that we have, we just
Python.
fix it, or Python, exactly, yeah.
And so that gives it prolonged life.
That gives it
beyond
life.
whatever is imagined for
It
it.
was only supposed to be 5 years, and we're at 25. And there's no expendables for like fuel and stuff like that we have to be concerned
It's just
with.
floating in orbit.
What about degradation? You talked about these photons bouncing
Yes.
down this barrel.
Yeah.
I would assume
Yeah,
that
that's a
even a
great
photon
question.
might have a little bit of an effect, like dripping water on a rock.
Honestly, most of the concern is because it's so sensitive and the sun is close to it. And so like there is issues with like how much it could warm up perhaps because it has to be kept very cool in order to observe these, capture these X-ray photons. So the sun is always kind of offering a bit of a danger, but there's lots of fixes for it. How it's pointing, where it's tilting, what it's observing at any given times. All the engineers are so clever to figure out the best way to keep it super efficient. All from the ground.
So
which exciting.
is there future plans?
Yeah,
Europe,
so
America?
there are new telescopes that are going to be coming on board. The Athena one is a European mission that will be coming in the 2030s, we hope. Doesn't still quite have the resolution of Chandra, however. So we are hoping.
Because it's European.
No, we're hoping to
honest.
plan like a super Chandra, right? Like a next generation Chandra. It's temporarily called the Lynx mission. And the idea is to provide an even larger area to collect the X-rays, even more high def, and that would just be a dream come true.
Well, that's brilliant.
Yeah.
And we look forward to just more reporting from, because you're doing something that none of us have ever met anyone doing what you're doing. So
Who knew this was a job? I
it's
don't.
like, what does mommy do? Well, I have to explain that. Hey, I'd like to offer some reflections on this evening and this content. If you look at the arc of science, progress in science over the centuries, in almost every case, advances in our understanding of the universe have arrived in the presence of some clever device, some clever new way to probe the world around us. And the people who do this, think about it. They were not content with all the previous ways that we were decoding the world. Our eyes were not enough. Our ears were not enough. So you find another way to do it, and you reveal that the universe is talking to you in these places that were previously ignored or had no clue they even existed. And so it leaves me humbled in the presence of what could still be discovered in the universe. Are we like William Herschel, just happy with the red, orange, yellow, green, blue, violet, and that's the whole world? And then, oh my gosh, there's another branch of the electromagnetic spectrum. Little did he know that exercise would continue. 100 years from now, will they be saying, little did Kim know that there's a whole other way to look at the universe, and back in 2024, we were practically blind? Is that what's missing in our understanding of the universe, forcing us to be blind to the 95% of the jelly beans in that canister? We know they're there. We don't know what they're made of. So I take this not as an occasion to celebrate how far we've come, but to reflect on how much farther we still need to go. That is a cosmic perspective.
And so beautifully said.
Thank you, Guild Hall. Chuck Nice. Kimberly Arcand. I'm Neil deGrasse Tyson, your personal astrophysicist. As always, keep looking up.